In this video, we're going to use a similar slicing strategy to find the volume of a cone of height h and bottom radius r. Adding those to the diagram here, it's important to recognize right off the bat that these are constants. The radius r and the height h are constants. I can't take a slice at height h, as we have done in earlier examples, because h has already been defined for us. So beware, in this case here, when we have generic values in the problem already that define the radius at the bottom and the height of the entire shape, we can't reuse those variables. That's an incredibly common mistake that students make on tests and practice problems. So, how are we going to tackle this problem? What we're going to do is take the same slicing approach we've taken before. We're going to imagine this cone being sliced horizontally. Why horizontally? Because when we do horizontal slices, we're going to get very nice shapes. In fact, we're going to get little discs. And when we talk about the volume of those discs, it's going to be a circle area times a thickness. That's how we can build a volume. Area times another third dimension, this little thickness here, gives us volume overall. But we need to define variables that aren't called h and r. And the easiest way here, I think, to do that is to define the distance down to a slice as y, and the thickness of that slice will be delta y. Where does that leave us? Well, the thickness is going to be straightforward. It's delta y. The circle area is also straightforward-ish. It'll be pi times the radius squared. Oh wait, we can't use little r. It's already been booked. It's already down here. So let us add to this picture here and this picture here a different radius. Let's call it capital R. We don't like really using other letters for radii. So capital R and capital R squared here. What we need, though, is we need that radius depending on the height, or this position y. We've chosen delta y as our integral variable, and so this has to be in terms of y as well. But fortunately, hiding in this picture, we have a way to convert. We have a triangle that is r down here at this side and h at this side. But we also have a smaller version of that same triangle, which is y high and which has capital R as that component of it. And if we're interested in capital R, that divided by y is going to be the same as little r over h. So there's no numbers in this yet, but we'll work it out. That means capital R is two constants, little r over little h, times y, which is a variable. And that we can then sub into our formula here. We'll have pi times, in parentheses, little r over little h times y, all squared, times delta y. What is that telling us again? This is the volume of one slice. If you tell me where you want to take your slice, down here at some value of h less than h, I can find the radius of that slice. That's what this formula here gives us. Once we have the radius, we do pi r squared to find the area of this region, and then we just multiply by the small thickness delta y to get the overall volume. We're going to copy this to the next page and continue on. So with this formula for the slice volume, what we then need to do is imagine adding up all the slices, and we'll go straight to the integral. The total volume is going to be what we get if we add up all the slices from the top to the bottom. We'll get there in a moment, but of literally this formula, r over h times y all squared, and the conversion factor is the delta y turns into a dy. Now if we redefine our variables for a moment, we're taking a slice at height y. The entire height of the cone is h, and so our first slice would happen at y equals 0. I could imagine if y was nothing, I'd be at the tip. I could take a slice there. And then I would use y larger and larger and larger and larger. The last y value we would have, this feels strange, but the last y value we would have is h. If my cone was height 5, I would go to 5. If it was 10, I would go to 10. If the cone height is h, we go to h. And that's it. We're ready to integrate. In fact, if you've checked up the volume of a cone before, you'll start seeing some things you can predict already. We're going to pull out the constants. We have an r squared and an h squared. Those come out front. We're going to be left with an y cubed dy. Remembering these are constants again. And what we should end up with is only an answer in terms of h and r, which will be perfect. The integral of y squared is going to be y cubed over 3. And I'm going to reinforce what the variable is here by explicitly saying y equals 0 up to y equals h. We plug in the top limit for the y value, and we end up with h cubed over 3 minus 0 cubed over 3. That looks a bit horrendous until we start canceling things. We have an r squared that doesn't get canceled. We have an h cubed over an h squared. That's one h left over. And lo and behold, we get the famous volume for a cone equation. Pi r squared times h over 3, or 1/3 pi r squared h. Notice how we built that. This is not an obvious relationship based on the geometry, but what we did is we said we can find the volume of a slice. Imagining it at different heights gives us different sizes, specifically different radii. We found the different radii, we multiplied by thicknesses, and that built us an integral. Once we got to the integral stage, it was just a mechanical calculation that spits out at the end of the day the volume of the cone that we were looking for. So a very powerful technique. The challenge here is working with these generic r and h values as constants rather than specific radii at the base here and height of the cone. But if you're careful and treat them as constants as opposed to the variable y, and if you're careful to define a variable that is useful for defining where you're taking your slices separate from h, it's a straightforward process.